Thank you. Thanks for this, for the invitation, and it's a fantastic workshop. Getting to know a lot of things, a lot of people, new subjects. Actually, I learned a lot from Zach just now about the material growth. So today, I want to give you a little bit of a different perspective on the material growth. I'm not going to dive into the MBE growth, but I will ask questions about MBE and just thinking hard about what are we trying to do, right? I mean, a lot of materials that usually grow with bulk, you have the luxury to make it complicated maybe, put 3-4 elements and try to sort of look at the phase diagram. In MBE, you can do that, but then the cost and the effort and everything goes up exponentially. So usually you tend to work with simple materials, like even if you can grow silicon on silicon, that's an achievement. So in some sense, it's kind of boring in terms of the material core of things, but then I will show you where sort of all the effort is and then why we want to even do that, right? Why do you want to even grow thin films instead of bulk? But it will be like half physics, half material. So this is my current group at NYU. We have a few postdocs, few students, and the data I present is basically a mixture of everybody's effort. We are funded by DARPA, Army, Intel, and a bunch of other agencies, but these two, the Army and the Air Force, are the ones that saved me at the beginning, following the discussion we had yesterday. When I started at City College in 2015, I had nothing, and the startup was smaller than anything that I could do. I got my PhD from Princeton, and Steve Lyon was my co-advisor. So when I went to City College, he said, "Don't you want to do MBE?" I said, "I'd love to, but I don't have any money." And he said, "I have one lying in the lab, lying around in the lab. Do you want to just take it?" And I'm not using it anymore. So I said, "That's a great idea." So we got this really old MBE. I think they bought it in 1979 or 81. And yeah, we moved it. I had no money to just transport it from Princeton to City College. So we put it in, there were like a few leaks. This is me and an undergrad down there who worked on the chamber, slowly came up, and then things, picked up slowly. That undergrad is actually now at Maryland. He's doing a PhD here, and I hear very good things about him. But I think that kind of goes back to yesterday's discussions that, when you work closely with someone, I mean, it's inevitable that you get a lot of experience, especially if you work with the advisor, right? Because then you hear everything firsthand. Now, once a group, grows, then things become secondhand. So I think if I was a graduate student, I would join a group that, the faculty is young and just starting. Okay, so things change, right? In 2-3 years, I moved to NYU. We have now a bigger operation. We have multiple MB chambers. This is part of our center now. That it has 7 chambers on it. We have ARPers. We have multiple MBEs, a sputtering, E-beam evaporator. We have adapters that can go between different chambers. We have other chambers in the next room. This particular one is actually joint effort. Andy Kent leads the effort, and Andrew, Dawood, and me are kind of helping out. So this is our chamber. Actually, that's the same chamber that got really, updated by time. And then, dilution fridges and all that. And now, that alone, we were alone at the beginning, but now we have many collaborations, many effort, and things now make sense. So let me now come back to the topic that I want to talk about, the MBE and thin films and why we want to do it. Before that, I'm just going to give you again some kind of motivation, which I think is interesting. There is a book called Singularity is Near. Maybe you have read it. It talks about how technology is progressing and where we are going. And in the y-axis is basically a figure of merit of the calculation, the power of computation, right? I mean, I don't believe the numbers is here, but it's just kind of a merit that is good. And the x-axis is basically the number of years, right? And if you just look at it, you will see that, yeah, in 1900, we really didn't have anything to calculate or save, any parameter. But then when we get to here, it kind of becomes more familiar that, especially here, the Pentiums and Core i7 and Core i5, right? All these things that we are currently using, right? But there is a very interesting, I guess, trend in here that, yeah, sure, everything is getting better. But why and how, right? I think if you notice now, there are these like dark regions and, white regions. The technology is changing every few years or decades or so, right? So there was a time that vacuum tubes were dominant, and they had a business. Their computers looked like a room, right? And you were doing things. And then the transistor got invented at Bell Labs, and then it just slowly changed everything, right? So then we went from these big rooms to smaller things, and then the ICs came in, the integrated circuits came, and then sort of that took over all the way, right? So this learning process is a generating, I guess, called, S-shaped growth versus time thing, that you are sort of happy in wherever you are, then you basically, there's a breakthrough, you go up, and then you saturate, and you're not happy again, and you want to do it again, right? So in time, at least in this book, is trying to argue that we're kind of near a transition with computation. And that kind of, I guess, agrees with Moore's law, and things cannot get any smaller. And so what is next? I mean, we don't know, right? I mean, maybe quantum computing, DNA, anything. But maybe it's an exciting time that something is going to change. And to just go back, again, on the same graph, we went from these to these, and something changed. And all of it is material, basically. Like all of this device and engineering and technology that is driven, at some point it was science, it was material science. People were looking at the basic elements of atoms and how to put things together to basically get some property that is we really like to get it out. And so it goes from studying one transistor, to getting like a full-fledged, computer. It takes about 60, 50 years, right? It's a long time, and a lot of effort and research that goes into this. So I think that 60 years owe most of its success to two things. One is that, we discover new materials. That's kind of bulk materials. That you grow, that they have new functionalities, right? And then the other one is that we can actually start to develop the material control. That's kind of like controlling interfaces as surfaces. Like for transistors, like the field effect transistor is basically a semiconductor like silicon, and then you have a gate on top, so you must have like a silicon dioxide, right? So people were working on this, in 70s and 80s, right, to just get that oxide better on silicon, right? And then eventually it led to, I guess, it was just a byproduct. The quantum Hall effect was, discovered all of a sudden, because they could make it so good that now they could see quantum oscillations and all that, right? And the second example, I guess, is obviously this gallium arsenide, that it just happened. It's just magical, crystal accident that, gallium arsenide and aluminum arsenide, they have the exact same lattice constant, and they grow within the similar growth methods and all that. So you can put them together. Now you can actually have interfaces between two different materials and come up with new devices like lasers and cell phones and everything that we have in high frequency. And that also led to fractional quantum Hall effect discovery, and another Nobel Prize went for that, just because we were so focused on getting something really good, right? So I think that kind of pays back, that focusing on even silicon dioxide is probably the most boring thing to do right now, right? But at some point it was important, and we figure it out and we move on, and then we keep learning that way. So most of my research somehow is connected to quantum computing or aspects of it. And I think this is kind of the same thing that is happening. Let me just skip this. So instead of a 0, 1, now we want to go to this qubit and then have full control over this new object. But it's kind of a reversed effect. Like with silicon, the classical bits, we started from material, we made them good, we found out these are good, for transistors, we went forward. With qubits, sort of the theory is always like, I don't know, 50 years ahead. So then you have to go back and say, okay, what can I do in terms of materials? Is there any advantage? What should I discover? And that's kind of a hard problem, right? It's like an inverse problem, right? If I tell you 3 times 7 is 21, it's actually easier to calculate that rather than I say, factor 21. Then you have to think more about how you can sort of do the factorization. Anyway, so we need materials, and to just tell you that this thing is just expanding. I mean, I'm sure a lot of you know about the hype and the buzz around this. There are about 44 startup companies. This is kind of the landscape that I think one of the best graphs that shows the landscape. Google, IBM, Microsoft, Intel, NASA, Rigetti, CIA, I don't know, Amazon, Volkswagen. Ford had just posted a job about the quantum engineer or what. Right, so there is a lot of interest and a lot of difficulty. I just want to tell you that it's at the material science point. So without material science, I don't think if this is going to, it's not. Sometimes you are so developed that it's just an engineering problem. This is definitely not. Any aspects of quantum computing still has a major material issue, right? So today I'm going to sort of pretend that we want to solve this topological, the Majorana topological qubit problem, right? And then just tell you what are the ingredients and what do we need and what we're doing, right? So in terms of material synthesis, you have to start from somewhere. You have to, pick your material. And in sort of thin film style, there are multiple options. So this axis is pressure, right? You can be at high pressures or very, very low pressures, the outer space pressures, right? So you can put things in a glove box, and I guess there was a photo from Jim Hohn's lab, right, for graphene and other things. Or you can have, a very expensive stainless steel chamber that there's no impurity in it, and the pressures are like 10 minus 12, right? And there's a gap in between that it's maybe even evaporator sputtering and all those things can cover it. So we usually work on this end because we don't want anything else to come to our material. But that doesn't mean that the other end is bad, right? I mean, let's say if you have graphene, if you do it in a glove box that has argon in it, right? It's very difficult to actually add other things in, right? Vacuum is good. But a lot of other inert material are also good. Like if it's all argon, 100%, so there's nothing else, and argon doesn't talk to your material, that's also a fantastic thing, right? Then the other opposite side is that there's absolutely nothing and only your material, which is also interesting. But the cost is amazingly different, right? Anyway, so you go back to actually our Bible, try to look at the materials that are there. The materials I've highlighted are the ones that we have in some chamber at NYU. So you have a mix of this. You can handpick the material that you want. But now you have to step back again, right? What do I want to do? And why do I want to do it? So it ends up, you end up with basics of materials. Like I have a crystal structure. I want to decide what I want to do. We are not bulk, so we want to do thin film. That means that you want to put one material on top of the other material, right? So, rule of thumb is that if the crystal structures are the same, and you just have a lattice parameter problem, right? Because they come in, different sizes. So if it's like a Lego, right? If some is bigger than the other one, it's not going to fit. You have to force it in. You're going to break things, and that's exactly what happens with these materials. So it happens. Almost 3/5 are zinc blende material. So basically that means the structure is the same. Now you have to play games with misfit dislocations and all that. There are some magical ones like gallium arsenide and aluminum arsenide that are perfectly similar. So the growth is kind of easy. And then there are ones that actually the structures are also different, right? You want to grow metal on a semiconductor. It's very highly likely that basically, one is FCC, the other one is zinc blende, and they just don't have any sort of fitting parameter. So then the game becomes, to be smart and then see, okay, maybe the lattices don't match, but maybe twice of that lattice matches one lattice size of the other one. Or if I grow it in a 1-1-1, now I can find some domain matching and all that, right? So those are very helpful, actually. So we can be guided by some simple theoretical models or MATLAB programming even, just asking for the lattice parameters. So we do a lot of that. But this is a quote from Pauli that says, God made the bulk, and the surface was invented by the devil, right? And it's kind of true that interfaces have their own nature, right? I mean, if somebody tells you, gallium arsenide, you have to think about two things. It's the bulk of gallium arsenide and the surface of gallium arsenide. There are two different things. Like indium arsenide, I will show you later, is a semiconductor. It has a band gap. It's like 0.37 volt EV, right? But the surface is conducting. It has nothing to do with the bulk that is gapped, right? So it's every material, the surface could be different than bulk, and that's very important, especially in MBE, because now you want to put two things together. So you have to actually mind that difference. So ideally, you look for this. Let's just start easy. Let's just start with gallium arsenide, aluminum arsenide. Everything is known. So what pressure, why do we want to grow it at the low pressure, right? What are the important factors? So you want to do gallium arsenide, you don't want any impurity, right? So let's say, so this graph actually is a very nice graph, I think, for showing for the ultra high vacuum, why is it important? So the x-axis is the pressure, right? So that side is high pressure, the right-hand side is very low pressure, right? And this axis, let's just focus on this, monolayer formation time. Right. So if you are at the high pressure, that means you have other things. Let's say for now it's just oxygen and we are just thinking about the oxidation of the surface. Right. If your pressure is, let's say, is 1 torr, right? So you are, you need about a microsecond to form a monolayer. There is like the first bonding of oxygen to a material, right? If you are down here at 10 minus 12 torr, that's what I was saying, like MBE can get there, right? The graph shows that it's going to take months or years before you're going to have something forming at the surface. And obviously this is very important for STM, that you want to look at the surface, you want to look at the first surface. But for MBE, basically, excuse me, you don't want anything else to come to that chamber. So you basically, one of the game, the main game is to actually get the chamber on the lowest pressure. To do that, you don't need water. So water has to go out. You have to bake the chamber. You want everything that goes in the chamber heated up above 200 C, so the water is out. There is no fingerprints inside the chamber, right? Only the materials that you need them. So we bake the chamber, we put 4 pumps on them, we put various pumps because each pump is actually pumping materials differently, right? A turbo pump is perfect for pumping the standard stuff, but not, it usually has a weight distinction. Cryo pumps are usually the good ones for these ion pumps. So in our chamber we have 2 cryo, yes?
What's the lowest pressure achieved in these kinds of chambers?
So below 10 to the 12 is actually, you have to now buy a very fancy gauge to actually be able to do it because the X-ray and the neutrons actually interfere with that. Lauren has got 5 times 10 to the minus 13 with a special gauge with this, yeah. But no growth, nothing at the beginning. The moment you turn on, then you got bad. 10 to the minus 12 is a standard, I think. Yeah. So that's great. And there's this thing we call, I guess, MB obsession. And I guess this is kind of a good summary. For electron mobilities, right? You make a quantum well of gallium arsenide sandwiched by aluminum arsenide, and you try to measure the mobility. At room temperature, actually, it's all below 10,000. Best materials, worst materials. Room temperature doesn't matter. It's dominated by other scattering mechanisms. But as you see, when you go to the low temperature, where we usually use these materials, at the beginning, like pre-1978, is all bulk, very low mobility. Then we learned to do modulation doping, undoped setback. Every single addition that you add to the MBE growth, it increases the mobility, right? So right now, the maximum mobility that has been reported by Lauren Pfeiffer is 36 million. That means the electron mean free pass is about 1/4 of a millimeter, right? So you have a 2D plane that the electron can go, 1/4 of a millimeter without any scattering, which is amazing. Just a single electron, right? And so in 1987, this whole thing really picked up around 80s. And there were like a handful of people who were doing MBE. Like there were not too many people. And Lauren, who is the master of this, was doing high energy physics, and somehow he gets interested to do MBE, and he became sort of the gallium arsenide icon for this. But there are but he was asking always the right questions. How do we get better? And that's his goal, like to get the best material and the best mobilities, right? So I have a question for you here. So the purest materials one can buy on the market right now is 99.9999989 pure. Is that how good or bad that is? What kind of background impurity do I get if I buy that material? And I can, the hint is, when the material sits on the surface, or the amount that you use, it's usually about Avogadro number per centimeter cube, right? So if you just do the math, so 10 minus 8 times 10 to the 23, you get about 10 to the 15 impurity per centimeter cube. That's actually a lot. In the best chamber, like Lauren Pfeiffer's chamber, the background impurity is in 10 to the 13, right? So it turns out that even with that kind of purity, this is high, but not all of them incorporate. So depending on what material you put in the chamber, you can actually have a very high impurity, background impurity, just because we don't have pure enough material. Right? And people have make their own zones that you'd evaporate and condense inside the chamber to get it better. But like aluminum is very difficult. Like it likes to form bonds to other things. Right? Some of them are easier, some of them are harder. But it's a difficult game. But luckily the best thing that we can do is 10 to the 13 background impurity and that can be achieved in the growth of gallium arsenide. If you do exact same thing with the best chamber and try to grow indium arsenide, this number 10 to the 13 is up in 10 to the 16. It's just because now you are choosing different materials, and the impurity levels inside the materials are different. It's a very subtle game that for each material you have to be focused. So unlike the bulk growth, usually people are stuck with what they set up the chambers to do. You cannot move too much. One of the interesting physics that people were looking to do was this fractional quantum Hall effect at 5½ that supposedly would bring you same Majorana physics and topological system. So this is kind of my growth sheet from 2009. And then the growth chamber, when I started, the growth was 1 times 10 to the minus 12. This is from Princeton when I was a graduate student. And this is how it works. Like we say just gallium arsenide between aluminum arsenide barriers. There are like so many layers. I don't know. It takes about 10 hours to grow this structure, and there are probably 1,000 lines in sort of coding to grow this, stop, and then go do that. This is the gathering layer, and a lot of things that go. But all of them are basically aluminum arsenide and gallium arsenide, right? So, but a lot of material goes in. We could grow mobilities on the order of 1 million. This particular one was our hero sample with an 18 million mobility, which is, it's not 36, but it's kind of respectable, right? And in this kind of, when you come to 18 million mobility, there are probably only like 5 machines in the world that can produce that kind of quality, right? Because you have to be very dedicated to this purpose. And MBE basically going forward for this. But it can be done, right? And especially, let's say you are interested in 5½ and some deep physics, you say, well, maybe it's worth it, let's do it, right? It's worse than that. So, sure, for observation of 5½ you need a very, extreme low temperature, very good fridge. There is no control knobs, this is your sample, right? It doesn't look very impressive. And there are very few machines that can do it. So if you are just a measurement person, you have to make good friends, and it's a very tight circle. But what you ideally want to have is that not extreme low temperature, just low temperature. You want many knobs, right? You want to make an interferometer. You need many gates to be able to independently control this, right? And you want like abundant and robust material heterostructure, right? At least you can cross-check different chambers, different people, different operations, right? But most of the time what happens is that, we grow the material I showed you, right? I send it to our collaborators. He puts a gate on. He cannot change anything. There is no quantum Hall effect. Everything has changed. And then, we keep arguing it's your fault or my fault. Or maybe you put something on the device that made it worse. Or, I don't know, your material was not good. Or you don't know how to fab this thing, right? And gallium arsenide, remember, this was the easiest one, right? This was the one that we could do well. But, the bar is very high, right? I mean, we can do a lot of stuff with gallium arsenide, but if you want to really say, I want a perfect picture, it's still difficult in gallium arsenide. So then it comes the time that you have to decide. You have to agree that materials, there are limited options of stacking. I cannot grow anything, right? I can just grow within my MBE. I have so many materials. I can grow so many of them. Misfit and dislocations add more complexity. Like if I want to grow indium arsenide and gallium arsenide, the lattices are different, 6.1 angstrom versus 5.6. And the controlling the surfaces and interfaces, that's an art by itself. So you have to really look at it, and the options are unlimited and the resources are limited. So you have to make educated guesses. On the other hand, when people make devices, there are numerous fabrication recipes, right? So all I want to say is that the device people have to be more flexible. Like when you grow a material, it's kind of set, and then we have to explore more in the device domain, right? Because things are easier. There are lots of etching and deposition tools just because the industry is so advanced, right? But on the MB side, things are very tight. Like I cannot grow everything. We cannot fab everything. I cannot put gates on everything. I just have to worry about that surface a lot, right? So hopefully, the device people learn from materials, not the other way. And now let me slowly, try to focus on one particular example that, how all of these little things are going to matter. And at the end, it's not going to look, it's a simple material, but that interface causes a lot of trouble. So topological materials have been interesting, right? Materials like bismuth selenide, are in the topological insulator category, and those are the ones that you can make them in the lab, right? You can just go and then synthesize, and there are like good data on them. There are another class called topological superconductors that have very interesting physics. P plus IP superconductor. But there are no good candidates that you can actually, or it's not clear that you can make them in the lab, right? And people try to look for those for a long time. And there are some candidates, but there are so many question marks, I'm not going to even get into it, right? And when 5-half effort, people got fed up with it and said, okay, this is not going to go anywhere. And there was no new material to really sort of like help us to get to this topological superconductivity. And the interest is that from topological superconductivity to making a qubit, there's a direct path. So topological insulators are interesting, but you cannot make a qubit out of it if you are really into topological quantum computation. And 5-half was one option, and there was like so many literature on it that people just say, okay, it's not going to work. Then there was an interesting idea. Somebody said, let's just write the Hamiltonian that we need, and then see how we can put things together that way. And instead of having one material that has everything, let's try to engineer something. Okay? So they wrote, this is kind of one of the simple Hamiltonians. I mean, if you know it, it's great. If not, then sort of I have it, broken in here. So it's based on this Kitaev chain. It's in one dimension, right? You need basically this chain to have Rashba spin orbit interaction, and that we know it in indium arsenide, indium antimonide, bismuth selenide. There are lots of materials with the strongest spin orbit interaction. You need a Zeeman field to lift the spin, right? So that could be an in-plane magnetic field that exists in the lab. So you have big magnets, right? And but in the same kind of material, you also need S-wave superconductivity. You need a proximity pairing. So independently, we also have those, right? Aluminum and niobium are good candidates, very simple. Indium arsenide, indium antimonide, simple. And then somebody said, okay, we cannot have all of them in the same material. Let's just put the one with this Rashba spin orbit here, and then put the S-wave on top of it. And if they are really close and the interface is perfect, maybe these guys talk to each other, and you kind of cook up that Hamiltonian at that interface. But now the interface becomes extremely important, because if that's where the Hamiltonian is going to happen, you don't want anything, impurity, or it has to be smooth, it has to be uniform, it has to be almost perfect, right? And then if this is true, then you apply an in-plane magnetic field, and then you basically have your Hamiltonian at that interface, and you can study it, right? And instead of going after a new material synthesis with the interfaces and surfaces, we try to basically simulate this Hamiltonian. It gets more, I guess, there are more conditions on it. To really get that Hamiltonian into an interesting regime, this is energy as a function of magnetic field. The field that you apply in the plane had to be greater than some field that is determined by the G factor of the material and the superconductor that you put on. So energy as a function of magnetic field. This is the Zeeman for indium arsenide. G factor is 15. So G factor basically tells you what is the slope. And this is aluminum gap, 240 microvolt. So when they cross, let's say in this case 0.3, 0.4 Tesla, you have the magnetic field has to be above that to drive you from a trivial phase to a topological phase. So that's kind of the normal thing. But if you change your superconductor and say, no, I want to use niobium, then you go up. Then now you are at 1.6 Tesla, right? That the whole game changes. So the choosing of the material is actually, choice is very important. But this also tells you, the superconductors usually don't like magnetic field, right? So aluminum critical field is like 50 millitesla at most, and you're asking for, I don't know, 300-400 millitesla, so it's not going to work. And niobium is kind of the same. I mean, you want 2 Tesla, niobium ITC is probably around the same number. So that's a game that we have to sort of, when we want to design our material, we have to solve this problem. But let me go forward and then tell you how we're going to attack this. So G factor is important, superconductor is important, chemical potential means that you have to be able to gate this device to sort of like put the potential where you want it to be. But let's start from the material first, right? Let's choose aluminum and indium arsenide, right? So we don't know anything about it. You look at the crystal structures, they are different. And the faces that we want to put on top of each other are going to be the bottom surfaces. So you look, just see what am I going to do. So this is your zinc blend, and this is aluminum in a 111 direction. Aluminum is FCC, but right now for this particular facet, we are looking at 111. That's why it looks like hexagonal, right? So you can just say, okay, let's just put it on top, see how it looks. That's how it's going to look. The reds are aluminum, the blues are indium arsenide, and there is no grade matching. I mean, this is by definition, and then you see things are kind of wandering around. And then indium arsenide lattice constant in this plot is like 6.1, right? Now let's allow that lattice parameter to change a little bit, right? Let's say if you have gallium, for example, the lattice constant is going to shrink a little bit. You can ask, you never get it perfect, right? The two materials are different, but what you can ask is that, instead of growing aluminum on indium arsenide, let's try to grow aluminum on an InGas, where X is the indium composition. Then I want to go back to this and then ask, how much strain do I have if I really want to push these materials together, right? So we can calculate that number, and that's the y-axis here. And 0 means gallium arsenide, 1 means indium arsenide. That's the graph that you get. And you see that around 0.8, there is a minimum of a strain. So you can say, hey, maybe that's the right number. If I want to put this together, maybe that's, I have the highest chance of getting this working, right? And you can look at that composition with that strain. You can say it's okay to have the strain at that lattice constant. And then you can see now, they find that they're sort of like the domains are not kind of matching. The blues are sitting on top of the reds with some kind of a symmetry, right? So now the energy that you need at that interface must be smaller and easier to grow at that composition. So 0.8 is kind of the good number we want to keep in mind, right? And if you want, you can also go ahead and grow aluminum on everything, right? I mean, we are experimentalists, right? So if you grow a very thin film of aluminum, 5 nanometer, on top of pure indium arsenide, right? This is what you get, is a bumpy, and sometimes it gets de-wetted, if you see here. And when you grow on 0.8, it's kind of flat. It keeps going, right? So you know that 0.8 is better than just indium arsenide. The white and the blacks are just because the aluminum now is in this hexagonal phase. So it has, if you look at the triangles that are coming down with aluminum, they can come into a rotation by 60 degrees. So there are two degenerate, basically aluminum 111 on that surface. So basically when they come, they don't know whether they should sit this way or that way. And those are the domains that they sort of like meet here and there. But in terms of transport or properties, it doesn't matter really. Anyway, so now that we can grow very thin aluminum, right? Yes?
How did this graph was calculated, the strain density, full strain?
Yeah, so basically you calculate the Poisson ratio if you basically allow things to, strain from one side and then expand from the other side. So there are actually 3 terms in that calculation, the self-strain, and the interface strain. And then you try to minimize that. So they are actually famous from 80s and 90s, and even if you look in our papers, there are supplementary that explains that. But it's a very simple calculation. The one that I showed you, this is a high school student calculation. That basically once you have the code, the MATLAB code, you can actually figure it out. So the power of MBE is that if we can grow layer by layer material, right, then you can choose to grow 2 monolayer, 20 monolayer, or 200 monolayer, right? So in this particular case, we want to obviously push the limit to grow very thin film, because if you need a magnetic field, you kind of know from the physics that the outer plane aluminum it's going to be always very low critical field. But if you can grow very thin film aluminum, when you apply a magnetic field in the plane, you are kind of in the paramagnetic limit of a superconductivity. And there is this thing called Clarkston limit for critical field that actually can kill that superconductor. And that is about 2.5 Tesla, 2.25 Tesla. So we did that. So this is the magnetic field being applied to the in-plane, the plane of aluminum, and this is magnetic field as a function of temperature, right? So first, if your bulk very thick, critical field of aluminum is here, TC is here. So TC is 1.2, and critical field, I mean in this graph, critical field is 0, exactly, right? So when you make it thinner and thinner, things just start to happen. Like the first thing is that the TC gets pushed up. So here you can see it's like 1.5 Kelvin, right, at the 0 magnetic field. And as you increase the field, this number goes up. At the lowest temperature in the dilution freeze, you can get about 1.5 Tesla, which is pretty good, right? We needed half a Tesla. And if you make it even thinner, 5 nanometer, then the TC gets pushed higher, around 1.6 Kelvin, and then with a critical field about 2.25 Tesla. Right? So is that the right field? In our systems, because the 2-deck is at the surface, that's where we want the 2-deck to be. The electric field is out of the plane. So for a spin orbit, it's in the plane. You can find a perpendicular direction to it. So it actually works. So in plane is actually a good number. Yes?
Is the TC increased?
Yeah. So it's, I don't think if there is a simple, I mean, I understood in the sense that it's been measured before, at least experimentally for me. Theoretically, I think there are a few explanations. I don't know it for this particular case because we think it's purely epitaxial. Yeah. But if you believe that you can make it amorphous, it always goes up.
I know that like nano aluminum has a high TC.
Right. So
is it some reduced dimensionality? And
I don't have a simple picture, but I think you can argue with some, the London penetration depths and this and that. It kind of really goes back to the basic, but it's phenomenology. I don't think if there's any microscopic, number in there. But for example, if you make this dirty, the TC also goes up to 3 Kelvin. So it's a Pandora box by itself. So let's say, we found out aluminum, the indium composition at 0.8 is a good number. And if I want that indium arsenide talk to my aluminum, my 2-deck or quantum well has to be at the surface, right? If I have aluminum here and 2-deck is here, they're not going to talk to each other, right? So I want some wave function overlap at the surface. So this is could be a proposed structure, right? Indium 0.8. I want indium arsenide somewhere. And we grow this on indium phosphide substrates. And another property of this 0.8, I will come back to it, and I will tell you that 0.81 is kind of a very also special number. But anyway, so you can also calculate something else. The thickness of how much do you need, right? I mean, I want indium arsenide to be kind of my dominant my quantum well, right? But it turns out, in a lot of things, I guess, metal has a very high density of state. Like they have a lot of electrons. Semiconductors, not so much. I mean, that's why they're semiconducting, right? So if you put them together, something like this, the superconductor is going to dominate, right? Basically, the semiconductor, the proximitized semiconductor is going to look like the metal because it's basically dominant. You have to put some kind of a barrier or slow things down to get sort of a convolution of both. And especially in the Hamiltonian I talked to you, right? Ideal case is that if you have half lifetime of those quasi-particles in one material and half lifetime on the other one. So you want that kind of energy scale to be on the rough scale. So one way to do it is that you can ask this question or calculate this WKB, the energy versus the in-gas widths for this particular composition. In the energy axis, this is the superconductivity, but this is the escape rate of the electrons, right? If you're down here, basically everything is in the superconductor. That's what kind of it says, right? So basically you have more properties of the superconductor. So it turns out, for aluminum, you have to see the Green's cross-section. That's about 10 nanometer. If you choose niobium, you go back down to 8 nanometer, right? So for any superconductors or any other material, there is some kind of an optimum thickness that will give you half lifetime in one material and half lifetime in another one, right? So for aluminum, indium arsenide, in gas, it basically turns out to be 10 nanometer is the right number to have the. So that's great. Let me also tell you why 0.81 was kind of an important number too. So you know that in most materials like silicon, gallium arsenide, if you put a metal on top, actually the electrons are kind of depleted from the surface and you get a Schottky barrier, right? That's kind of a standard textbook thing. And that is true because the Fermi level at the surface of those materials are pinned in the band gap, right? So this is the band gap. The Fermi level at the surface is pinned in the band gap, right? Don't confuse bulk and surface. Surface is on this side. This is the. And indium arsenide is an exception because the Fermi level at the surface is above the conduction band of indium arsenide. So if you put a metal on indium arsenide, it's just going to conduct. So you have carriers already kind of floating on indium arsenide surfaces. You just buy a wafer, it's just going to conduct, right? So, but that's a good thing and a bad thing. It's a good thing because you can now make it talk to a superconductor like aluminum that we talked about. It's a bad thing because the bending is so much, it's 100 MeV, right? That the carriers, you can never gate them, you can never control them. You basically have a bunch of carriers sort of sitting at the surface, uncontrollable, right? If you know, I don't know, if you sneeze, humidity is up or down, the density goes up and down. And you can actually do that experimentally. If you put it in an ammonia and then take it out and by time measure the density, it's actually changing in a very nice format. So there is the crossing. Gallium arsenide is a Schottky barrier, right? You see the this is the Fermi level, the pinning. This is the band gaps, right? Here we have Schottky barrier, indium arsenide, we have ohmic. So there must be a crossing, right? If I plot in gas as a function of the Fermi pinning, right? At the beginning I'm in the gap, and then at some point I cross the conduction band, and then I become pinned in the conduction band. So that crossing point is 0.85, x 0.85, right? So if you are below 0.85, you are kind of in a very low Schottky barrier limit that you need to put a little bit of dopant, and then you have a very controllable quantum well near the surface. So if I go back here, that's why this sort of silicon doping is there, right? Because you want a quantum well. If I make this with gallium arsenide, there's no way I can dope this because the Schottky barrier is so hard that I cannot bring electrons to the surface. But if I grow this such that everything is close, by a little bit of doping, I actually put electrons in the quantum well. So 0.81 is good for aluminum. It has the least strain. It's perfect because I can grow this with 10 nanometer. It's not like half a monolayer, or it's not like 100 nanometer. It's also great for this tuning that we'll see later on, that how we can tune the numbers. So you can grow. Again, experimentalists, we know that the calculations are good, but you always have to try everything, right? So 2 nanometer, 10 nanometer, 20 nanometer. And what I'm showing here is the quantum well near the surface and the charge distribution in red, right? So 2 nanometer, you have a lot of overlap at the surface. 10 nanometer, this is decaying. 20 nanometer, maybe I'm already not talking to aluminum anymore, right? And then you can also look at the aluminum arsenide, 2 nanometer, 5 nanometer. But the interesting thing is that, you know, for the 10 nanometer InGaAs that we liked, we can actually get mobilities on the order of 44,000. These are kind of our highest mobilities that we can get. Let me show you some data. I took it out. But basically, the mobility now, the maximum reaches at 50,000. We can actually characterize the background impurities, the interface, the alloy that we have in the chamber. What are these? How will each of these will limit the mobility of my sample, right? It turns out, not surprising, is all surface scattering, right? Because your now quantum well is near the surface. That's kind of the dominant effect. Basically, everything else that mattered for gallium arsenide and other things are kind of not playing that much of a role. And in addition, we sacrifice this, but we get a ticket, and that's a strongest spin orbit, right? You are now at the surface. There is a huge electric field. At the bottom of this, you have an offset of 300 MeV, but at the surface is infinity. The barrier is infinite, right? The electrons cannot hop out. So you basically get a huge electric field across the quantum well, and that gives you a huge Rashba. And that you can measure it in anti-weak localization measurement. So this is conductance, correction to the conductance as a function of magnetic field. You can fit it, you can get numbers. If you change the density, alpha as a function of density, it sort of like keeps going up, right? So that's good. It's the standard characterization and all that. So to sort of a recap, I guess in half of the talk, hopefully it's half. My time's up. Almost. Okay. 5-10 minutes. Okay, I'm gonna now fast forward a little bit. So we have larger scales. We grow on wafers. We have a spin orbit with semiconducting with indium arsenide has a semiconductor with a stronger spin orbit. Superconductor is pure. We get good interfaces. TEM images show nice interface. So let me show you the proximity effect in this material, and then you have all the ingredients, and maybe you can put them together. So people have been growing, doing these kind of things. Niobium and indium arsenide from Santa Barbara. Herb Kromer actually did quite a bit of this. Jim Allen also tried that. But this is a sort of a text from Jim Allen's student, Conrad Leonard now. That basically he said, I made a lot of devices. Some worked, some didn't work, but we never figured out why not. Probably interface is the problem. And the difference is that with us is that these quantum dots are buried structures. They're 50 nanometer below the surface, right? So putting a superconducting contact means that you have to etch down and then put the superconductor here. Here we are growing at the surface. Mobility, as you can see, is very different. It's 2 million here. We are 0.05, right? But we can put epitaxy in this, while here you have to do the device fabrication, right? So it's going to go back to my first thing. So then the way that you can sort of characterize proximity effect, the easiest one is Josephson Junction, that probably Jimmy is going to also talk about. So you have, in a standard oxide junction, you have an insulator. Now we have a semiconductor sandwich with superconductor. But the advantage is that because it's a semiconductor, now you can gate it. In an insulator, you're kind of set by the design, right? Once it's 2 nanometer, all the numbers are there. You can play games with the surfaces and all that. So this is an image of our SNS junction, right? So this is aluminum. And this little thing is where aluminum is peeled off, right? And then now you put a gate on top of the whole thing. So the game becomes grow this thing, make Josephson junctions with a gate on top, put it in the sample holder, put it in dilution fridge, and measure them. And if you are familiar with Andreev reflection and bound states, basically the bound states in the junction, this is the superconductors, this is your indium arsenide channel. The bounded states will carry the supercurrent, that is IC. That gives you how the structure is good. And the Andreev reflection is kind of a one-sided effect. If you have one SN junction, you can basically get something that is excess current that comes from the extra contributions of this Andreev reflection, and basically gives you the contact transparency, right? All I'm arguing, my interface is good, my interface is good. I have to show you that by some measurement, right? So this is one of the samples. This is an AFM image of how the surface looks. We cannot get this flat. This is a misfit problem, right? Indium arsenide has a larger lattice constant than indium phosphide. So we have to deal with that surface that is a few nanometer rough. This is the quantum Hall effect, RXX as a function of magnetic field for these samples with 10 nanometer barrier at the surface. To me, it looks pretty good. It's not as good as the gallium arsenide that we used to grow, but now it comes, we can do superconductivity. And this is the voltage as a function of current for this one of these SNS junctions. And you can see that at high biases is kind of a line. It's Ohm law, right? VIR. But then at some point, things start to deviate, and then you see sort of a zero voltage state that we call supercurrent, right? The supercurrent here in this case is like 5 microamp, which is pretty substantial. We can grow a lot of materials. You can now look at the mean free path, coherence lengths, and then say which one is in the ballistic limit, which one is not. Let's just focus on this one that we know is in a short ballistic regime. That's the simplest to actually analyze. And before I do that, let me just give you some idea for those who were not doing epitaxy of interface, so we can compare ourselves to them. So Leonard's dissertation that I talked about and Klapovic group, they have done a lot, Santa Barbara and Delft on this. And this is one of the beautiful works actually from 1998 that basically they measure multiple devices, measure supercurrent resistance. If you normalize it with the gap, they get 0.05. And that was kind of the standard number for most of these junctions. What you expect for a short ballistic is pi delta, right? Delta is the gap and pi. So you needed this to be 3 point whatever, and now it's 0.05. That's not good. Something is wrong, right? So this is kind of the summary of our data. So this is ICRN as a function of delta, the normalized lengths. This is at least the data from Hayda et al. And this is the epitaxy samples at NYU, right? So now we get up to 2, maybe more than 2, times delta. It's not 3, but at least it's good, but it's way, way more than the 0.05, right? So it kind of says, mobility is a great thing, but for some things, interface is better. Just sacrifice the mobility, but get the interface right, right? And that has led to a lot of new effort in various things. I think I'm just going to skip a few things now. So you can do ICRN as a function of temperature, right? You get a relationship. And you can sort of fit formulas to this. And if you believe me that this is the right formula for ballistic short junction, tau in here is the transparency. I didn't try to fit this formula to that. I'm just plotting t equal to 1 in dashed line, right? So it looks pretty good. Maybe it's not exactly 1, it's 98, 97. I mean, it depends on the functional form. But it's a pretty good transparent junction. And we have more results from a squid that we can actually look at how transparent these things are. So one quick application before even we get to Majorana and all that, right? When you do science, research, you usually stumble on things that, it just branches off into its own thing, right? So this is one of them. This is a semiconducting junction, right? So at 0, we have the supercurrent. But now we can apply the gate. You can deplete the electrons in the channel, and obviously now things shrink, and then at some point there is no supercurrent. So basically you have a Josephson transistor that you turn it on, supercurrent, turn it off, 1 kilo ohm, like 0 ohm, 1 kilo ohm, 0 ohm, 1 kilo ohm. So we actually, with Intel, this is kind of a project that we're making some Joe-fed circuits that you can make like devices, and then this is an inverter, for example, that you basically put pulses in. And this device, the Josephson Junction, actually inverts it. And we have made a lot of this, and you can just do some technological thing. With Charlie Marcus, with these samples, this kind of samples, we have measured signatures of Majorana fermion, which is basically based on this zero bias peak. It's interesting, but obviously it's not the final verdict on this. So things come together in some sense, but I want to show you sort of the next thing in the next 2 minutes, that what are we doing, right? We are not done. So the magnetic field that you have to apply, the global magnetic field that we talked about, right, is great, but it's going to be a problem if you want to ever make many of these. You want to have local control. You want to bring it in microwave, right? You don't want a big magnet, applying to the sample. Even if you have a computer, you're not going to have like a 2 Tesla magnet next to your computer if it ever works, right? So we have actually started a big collaboration on how to add magnetization to this. So now we are making these films. These are like cobalt platinum films that actually go below the quantum well on indium arsenide. And by applying a magnetic field, you can actually break down isotropy. I mean, ideally, I wanted this to be our parallel lines. So that's what the simulation is for. But you can imagine if I put the nanowires, it's going to be kind of periodic, right? Because nanowire is kind of a small dimension. And then we have proven that we can get Majorana fermion. You can actually turn this on and off. And we are growing this kind of structures. But for sake of time, let me also show you the next idea that, if you now go from these thin films and now you cut them into these nanomagnetic pillars. These are sort of 2 domains of magnetic texture separated by some sort of an insulator or a metal that can be turned on and off electrically, right? So if you basically, this is the off position, they are anti-parallel. In the on position, they are parallel, right? So you can now have like anti-parallel, parallel, 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 anti-parallel. And we have shown that from the fringe field of this into the 2-deck, you can actually create a Majorana Hamiltonian again. So you can exactly get the magnetic field that you needed. Plus some extra spin orbit field because of the texture. It's helical. So you can get that. You have this is sort of the pink is your average Zeeman. And then the blue is your kind of rotating magnetization. And then you can turn it on and off. You can turn on this to be parallel and then turn off the next one. So your Majorana pixel is going to grow by 1 pixel. So you can grow things, you can move things if you want to. So we are working toward this. We have made devices. Let me skip this. We have shown that, okay, obviously if you can move things now, you can do braiding and fusing, which is very exciting. This is an actual TM image of these NMPs. So these are the magnetic pixels that I was talking about. They are about 50 nanometer in width and 50 nanometer space from each other. So you can make a lot of these and you can turn them on and off. Now the challenge is exactly how we need it to be really close to the 2-deck, and we are working on that with sort of a combined epitaxy that we grow indium arsenide aluminum. We give it to Andy in the bigger chamber, and then they put aluminum oxide and some other metals. So it's all good. But you sort of like come up with various just like 4 slides of what are the future things and how the material can help. When my high school student was playing with that code, she said, if I grow niobium 110 and indium arsenide 111, it kind of looks like a strange star-shaped lattice that you can say maybe it's a Kagome lattice. And then if you can, now we have like another person to sort of like look at this to see if it's relevant or not. But the basically is that you have indium arsenide 111 and you grow one monolayer of nickel 110, and then you may get something interesting, right? So that's I think these are kind of the things that MB can do well if you can control it. So for measurement, you obviously go to dilution fridges. For this Majorana fermion, G factor was important, right? G factor 15 was this slope. If it is 100, it's come closer. That means the magnetic field that you needed now is going to go to a lower field, right? So one of the highest G factors in indium arsenide and antimonide 3,5s is indium arsenide 50%. And we have grown this, and the quality R versus magnetic field looks decent. We have made Josephson junctions that show supercurrent and all that, so we have all of that. The last one is silicon. All of these happen because we have different materials growing on different materials, right? So the surface roughness, the mobility, everything. But what if there is a material like silicon that you can make it superconducting and then grow it on silicon, and then you decide not to dope it, becomes an insulator, and then you dope it to become superconductor, and then it's homoepitaxy, basically, right? So this is kind of the motivation for this project. So in this one, we have silicon. We grow silicon gallium doped, and then we anneal it. And basically, this is resistance as a function of temperature. For some annealing, we actually get no superconductivity. For annealing about 7,600 degrees, we get a TC of about 6 Kelvin, right? Gallium superconducts at 1 Kelvin. Silicon obviously doesn't superconduct. So this is a kind of a new superconductor with 6 Kelvin superconductivity. We can debate whether this is, what kind of superconductor it is. But now we are going forward to make this kind of a structures, that this is a superconducting layer, grow like a not doped structure, and then grow another doped structure, and then need the whole thing, and make a vertical Josephson junction. Everything is homoepitaxy, so you don't expect any misfits and all that. So we're having fun. Lots of theory. You do it, it comes out usually wrong, but you sort of stumble on something else, and then there are so many materials to try on other ones, and it is, each of them will come up with something surprising. Thank you.